And in this sixth and final video, we're going to dive deeper into Dalton's law of partial pressure. And one really important application of this is anytime we're collecting a gas in a chemical reaction, we will typically collect that gas over water. This leads to an unavoidable consequence where some of that water will evaporate and there will be water vapor mixed with the gas we're trying to collect. If you look in this reaction chamber, we're trying to collect hydrogen gas from the reaction of hydrochloric acid with zinc. However, water will evaporate into that chamber because we're collecting this gas through water displacement. And since this problem is asking us to find the total pressure of gas inside the chamber, that means we're ultimately going to have to find the pressure of the hydrogen gas and then the pressure of the water vapor, and then add those two pressures together using Dalton's law. Let's start first by finding the pressure of the hydrogen gas produced in the reaction using stoichiometry. And just like with any other stoichiometry problem, we need to start with a balanced chemical equation for the reaction. Then we will find moles of hydrogen gas produced in the reaction. And this is done with simple stoichiometry, where we take 3.00 grams of zinc divided by its molar mass, multiply it by the mole ratio, which is a 1-to-1 ratio, and we end up with 0.04587 mole of H2. And now that we have the moles of H2, we can find the pressure of H2 gas by using our PV equals nRT equation. But now there's a really important point I want to emphasize. Whenever we're using the PV equals nRT equation, the pressure that we're solving for is the mole value that we place into the equation. So if we're putting the moles of hydrogen gas into the equation, then we're finding specifically the pressure of that hydrogen gas. This won't matter when we're only looking at one gas, but whenever there's a mixture of gases, whatever the mole value identity we're putting in for, that'll be the pressure identity. So we're putting in moles of H2, we'll find the pressure of H2. If we put in the total moles in a chamber of a mixture of gases, we would be finding the total pressure of the gases in that chamber. So now we can put in our values, given that we found the mole of H2 above, and solve for the pressure of H2 in this chamber, which the pressure of H2 in the chamber will be 0.110 atm. Now that we know the pressure of the hydrogen gas produced in the reaction, in order to find the total pressure, we need to find the pressure of the water vapor. And it turns out that when in a closed container, the amount that the water evaporates is based off of the temperature of that environment. And at a given temperature, water will always evaporate until it reaches a certain pressure of the vapor above that liquid. Since this reaction is happening at 20 degrees Celsius, the water will evaporate until the vapor above the liquid generates 17.5 millimeters of mercury of pressure. Now, exactly why this happens has to do with a concept called equilibrium that you'll learn about in a higher level chemistry class. In practice, we could use these reference tables to find out what the vapor pressure of water will be at a given temperature. Now, to use this value, we will have to convert it into ATM by knowing that 760 millimeters of mercury is 1 ATM. And then now we can calculate the total pressure by knowing that the total pressure is just the sum of the pressure of the hydrogen plus the pressure of the water vapor. And so that gives us a total pressure of 0.133 ATM. And so again, this concept of Dalton's law is that the total pressure of a mixture of gases in a container is just the sum of the individual pressures of each gas. But probably the most useful application of this is knowing that since every gas in the mixture will have the same temperature and will occupy the same volume, the individual gases in the mixture only really differ by the amount of that gas present and therefore the portion of the pressure that that gas will represent. And so, like I said before, with PV equals nRT, the V, the R, and the T are all the same. So they're really only the moles and the pressure are the difference. So if I have the total moles, I'll get the total pressure. But since our total moles is really just made up of moles of nitrogen and moles of oxygen in this example, our total pressure is just made up of the pressure of the nitrogen and the pressure of the oxygen. And it turns out that whatever portion the nitrogen is out of the total moles, that's the same portion that the pressure of the nitrogen represents out of the total pressure. And that's really the powerful part about Dalton's law. It's that if you know what portion of the total moles a gas represents, then you also know what portion of the total pressure that same gas it represents, because those two values are equivalent. And if we truly understand this relationship, we're going to find it super useful in a lot of chemistry applications. Sometimes we can best understand a new concept through some practice problems. So let's try each of these to see if we can really start to understand Dalton's law. So this first problem is pretty simple. We have the partial pressure of three gases, oxygen, carbon dioxide, and helium, and we want to know the total pressure inside the container. We simply add up the individual pressures and find that the total pressure is 9.00 atm. Now this next problem is a little harder. We know the total pressure, and we want to know the partial pressures of each of the gases. In this mixture, we have oxygen gas and helium gas. Now, according to Dalton's law, we know that the fraction of the portion of the total moles that is oxygen will be the fraction of the total pressure that is oxygen. And the same would be true for helium. The fraction of the total moles that's helium will be the fraction of the total pressure that's helium. So the first step in this problem is finding out how many moles of each gas is present by converting the grams into moles. And even though we have equal masses, we do not have equal moles because oxygen is 32 grams per mole, where helium is only 4 grams per mole. But by adding the moles together, we find that there's 11.25 mole of total gas mixed in this container. And since we know the portion of oxygen moles to total moles is equivalent to the portion of oxygen pressure to total pressure, that tells us that the partial pressure of the oxygen in this mixture is going to be 0.100 atm, which means that the remaining 0.800 atm must be coming from the helium. In this next problem, we have nitrogen gas being collected over water at 40 degrees Celsius. We are given the total pressure, and we're also given the vapor pressure of the water at 40 degrees Celsius and asked to find what is the partial pressure of the nitrogen. So again, with Dalton's partial pressure law, we know that the pressure total is equal to the sum of the nitrogen and the water vapor. So we can input our values, which were given in the problem, and then we could easily solve for the partial pressure of nitrogen, which would be 92.04 kPa. Since the total pressure was given in kPa and the pressure of the water vapor was given in kPa, we didn't have to convert any pressures for this equation to be true. Okay, now in this next problem, we have three gases, methane, ethane, and an unknown amount of propane. And we have the mass of the methane and the ethane, but we don't know how much propane we have. They're all in the same container, all at 23.0 degrees Celsius, and we know the total pressure of the container is 4.43 atm. Now, there's a lot of ways we can solve this problem, but they all come down to this equation right here, where N1 over N total is equal to P1 over P total. Let's start by calling methane our gas number one. A simple molar mass conversion will tell us that we have 0.498 mole of methane present in this chamber. And at first, it's going to seem like we only have two of the four values needed to solve for this problem. But in fact, we actually can solve for the other ones as well. In fact, it's really easy to find N total, the total number of moles. Because you may recall from earlier in the video, I said that the moles and the pressure in this PV equals nRT equation are linked. So if you know the total pressure, you can actually solve for the total moles, which in this case would be 1.82 moles if I were to solve for N, given that the total pressure was 4.43 atm, the volume was 10 liters, and the temperature would be 23.0 degrees Celsius plus 273 to be 296 Kelvin. And now that I know the total moles of gas present, I can use this equation to solve for the partial pressure of gas number one, which in this case was our methane. And when I do that, I see that the pressure of the methane gas was 1.21 atm. I can then move on to my second gas and find out how many moles of ethane I have, which would be 0.598 mole of ethane. And I can use the same relationship. Now I'm just going to say moles of number two, which is ethane out of the total moles, is going to be equal to the pressure of number two, which is ethane out of the total pressure. And since now I have moles too, I have total moles still, and I have total pressure still, I can easily solve pressure number two by doing all the same math, and I'll find that the pressure number two, which is the pressure of the ethane gas, will be 1.46 atm. And then finally, pressure number three can be found just by knowing that the total pressure must just be the sum of the three individual pressures adding up to make that full pressure. So then I'm going to find the propane gas here. The third gas is going to have a pressure of 1.76 atm. And I'm done. And in this last problem, we have a mixture of oxygen and nitrogen gas that's going to be 32.8% nitrogen by mass. Now, the problem is just because that's the percentage by mass does not mean that'll be the percentage by moles because nitrogen and oxygen weigh different amounts. And in order for me to use this equation to solve for the partial pressure of the oxygen, I need some ratio of how much oxygen in moles there would be if I knew the total number of moles. But now here's the trick to this problem. This ratio will be the same for any total number given this percentage. As I increase the total amount of moles, the oxygen would still just be that same portion. So that would grow proportionally. So regardless of how much I have, if it's 32.8% nitrogen by mass, that'll always be the same portion of nitrogen and the same portion of oxygen. Mathematically, I just need to define an amount that I have just to solve the problem. So I'm going to assume I have 100 grams of gas. And if I did, that would mean I would have 32.8 grams of nitrogen in that gas and 67.2 grams of oxygen in the gas. A quick mole conversion would mean that that would be 1.17 mole of nitrogen gas and 2.10 mole of oxygen gas for a total of 3.27 mole of gas entirely. Now, I want to emphasize that this is not necessarily the amount of all these gases actually present, but since it's 32.8% nitrogen by mass, any amount that I would have would fall down and end up being these same portions. Well, yes, the total amount of gas may increase or decrease, but the amount of nitrogen gas and oxygen gas would also increase or decrease proportionally. And we've seen this a lot this year, percentages, how we could use 100 grams of the substance to make the math easier. And now that I have these number of moles of oxygen in total, I can plug them into this equation, leaving me only with the variable of the partial pressure of oxygen, and that's going to be easy to solve, which it turns out will be 504.1 millimeters of mercury.